Welcome to the Deep Dive, where we crack open stacks of sources and extract the most important nuggets of knowledge. Today, we're putting on our detective hats and inviting you on a kind of ride-along investigation. We're diving into the surprisingly messy reality of solar power generation. You often hear these catchy phrases, right? Like solar works everywhere, or maybe just slap some panels on your roof and you're golden.
That sounds easy.
It sounds wonderfully simple. But our hunch, our strong suspicion really was that this generic story, especially about solar capacity factors, like that often quoted 20% is typical, it's just, well, it's far too simplistic.
Yeah,
it can actually be incredibly misleading.
What's truly fascinating here is how easily we fall for those broad averages. I mean, an average capacity factor from some well-known solar farm in, say, Arizona.
Right.
It tells you absolutely nothing about the actual solar potential in your city. It won't help you size an off-grid project in rural Senegal or, accurately estimate the energy you'd really get from a rooftop in bustling Cairo. The sheer, often overlooked, differences in solar potential across the globe. That's really what sparked our investigation.
Exactly. This wasn't just a hunch for us. It felt more like a case we needed to crack. So, okay, let's unpack this a bit.
Let's do it.
Our mission today is to take you right into the passenger seat of our very own solar variability dashboard. It's this custom-built data vehicle we engineered to reveal some truly surprising truths.
Yeah.
We aren't here to teach you how to code or anything like that, but we are here to show you what we found when we really dug deep into the real-world data.
We just couldn't rely on those generic numbers anymore. It wasn't precise enough. To get actionable insights, we knew we had to build our own system.
Right.
So today, we're excited to present the findings from building this practical solar variability dashboard. We analyze patterns and unlock some critical insights from locations as diverse as Dakar all the way to Oslo.
Okay, so you've highlighted how misleading those averages can be. But for someone just starting out, or maybe even an experienced investor looking at new markets, what's the biggest misconception that your data vehicle, this dashboard, immediately shattered? I mean, why did we even feel the need to custom build our own toolkit?
That's a great question. And it comes down to impact. That 20% capacity factor is typical, quote, you hear.
Yeah.
Like you said, it's often useless because it hides this world of variability.
Yeah.
For you, the listener, here's why digging into the real data matters so profoundly. First, and most critically, it's all about location, location, location. Your actual solar generation isn't just about whether the sun is generally out. It depends heavily on your specific latitude, the local weather patterns, the climate. I mean, think about it. Oslo is dramatically different from Cairo.
Completely.
Nairobi is fundamentally not London. These aren't minor variations. They dictate pretty much everything.
And that leads directly to design decisions, doesn't it? If you know your precise solar resource, not just some vague average,
Exactly.
it helps you accurately size everything. We're talking battery storage systems, planning for necessary backup power, creating reliable revenue estimates for project financing.
Right.
Imagine this, a difference of just a few percentage points in capacity factor that can literally make or break the economics of a whole multi-million-dollar solar project. It's that significant.
Which then flows right into investor confidence. When you can actually present month-by-month generation estimates based on real, granular data.
Not just hand-waving.
Exactly. Not just hand-waving about sunny locations. Investors pay attention to that. That level of detail inspires confidence. And finally, for the large-scale grid operators, the ones trying to keep the lights on for whole cities, understanding grid integration is absolutely crucial.
Yeah.
Knowing your location's daily and seasonal variability patterns helps predict the impact on the larger electrical grid. Are you looking at gradual, easy-to-manage, dawn-to-dusk transitions? Or are you facing sudden cloud fronts that can cause abrupt, massive power drops? These rapid shifts, we call them solar cliff events. They truly make grid operators incredibly nervous.
Those solar cliff events sound genuinely terrifying if you're trying to keep a city powered.
Yeah.
So to truly understand these abrupt changes and all the nuances you're talking about, you must have needed some pretty specialized tools, right? What was in your investigator's toolkit?
Absolutely. Yeah, to really map the solar landscape and capture every detail down to the hour, we needed specialized instruments. We couldn't just use a general-purpose spreadsheet.
Right.
We used professional-grade libraries. These are really the gold standard in the industry. For example, for the actual solar calculations, figuring out how much energy a panel produces based on sun position, weather, all that we used PlipLib.
Okay.
Think of it as our professional-grade microscope for solar data. It lets us precisely calculate energy generation down to the minute if needed, though we focused on hourly.
And once you've generated all that data, I mean, I can only imagine the sheer volume. How do you make
Yeah.
sense of it?
Exactly. Tons of data. So to organize and sift through that mountain, we're talking millions of rows of information. We relied heavily on pandas.
Ah, pandas.
Yeah, it's like our superpowered digital filing cabinet and analysis engine. It lets us find patterns, perform complex calculations really, really quickly.
Okay.
Then, to visualize our locations on maps, to give us that geographical context, we integrated Folium.
Got it.
And for the final presentation, turning all that raw data into clear, compelling, interactive charts that let you zoom, pan, explore the evidence. We leveraged Plotly.
So that's the dashboard itself.
That's the engine behind the dashboard. Yeah, it was like our high-tech evidence board, making complex data immediately clear and interactive. This combination of precision instruments really allowed us to gather and analyze the evidence with confidence.
Okay, so with these sophisticated tools in hand, you started your investigation. Let's open the case files. What were your suspects, or maybe your 6 key study locations, and why pick these specific cities?
Right. We defined 6 diverse cities across 3 continents. We wanted a representative sample of global solar challenges and opportunities. First up, Dakar, Senegal. Tropical savanna climate. Lots of sun, sure, but unique challenges with seasonal dust storms, significant variations in cloud cover.
Interesting.
Next, Nairobi, Kenya. Subtropical highland climate. Here, we saw interesting altitude effects and a unique bimodal rainfall pattern. 2 rainy seasons that impact solar output.
Okay.
Then we have Cairo, Egypt, classic desert climate, incredible sun, obviously, but facing challenges like extreme heat and occasional sandstorms.
Makes sense. And then moving south.
Shifting south, we looked at Cape Town, South Africa. That's a Mediterranean climate. Its key characteristic is winter rainfall and significant coastal clouds during those cooler months. Very different profile.
Right. Then Europe.
Up in Europe, we selected London, UK, the quintessential oceanic climate, really, characterized by persistent, often thick cloud cover.
The London fog stereotype holds true for solar, then.
Pretty much, yeah. And finally, way up north, Oslo, Norway, humid continental climate. Here, the extreme latitude means significant winter darkness and very low sun angles for much of the year, a real challenge.
So quite a range. Why these 6 specifically? What was the strategy?
We chose them for very specific reasons to make our investigation robust. First, they cover an extreme latitude range, right? From 60 degrees north in Oslo all the way down to 34 degrees south in Cape Town. That gives us a full spectrum of how the sun's angle affects generation.
Okay.
They also represent a huge climate diversity desert, Mediterranean, oceanic, continental, tropical savanna, capturing nearly every kind of weather pattern you can imagine.
Right.
And finally, we included a mix of developed and developing markets. Each has its own energy needs, its own grid challenges. It makes the findings truly global and applicable, we think.
So for each of these suspect cities, how did you collect the evidence? You mentioned millions of rows of data. How did you actually simulate the solar conditions for a whole year?
Right, that's where our PlipLib solar microscope really came in handy. For each location, we simulated a full year of hourly solar data for 2023.
Hourly? Why hourly?
Yeah, hourly. It's kind of the sweet spot. It's detailed enough for good accuracy, especially for capacity factor estimates, but it's still manageable in terms of computation time and data size. Going more frequent, like every minute, doesn't significantly improve the big picture metrics we were after.
Gotcha.
So this simulation included clear sky irradiance calculations. That's basically what the sun would provide with 0 clouds. Then, crucially, we layered in a simplified cloud simulation based on each city's typical climate. So desert climates had rare clouds, oceanic climates had much more frequent and dense cloud cover, and so on.
Ah, okay, so it's like you collected an entire year's worth of detailed surveillance footage for each city's solar exposure, accounting for typical weather. What specific data points were you capturing in that footage?
Precisely. Yeah, the data points were pretty comprehensive. We captured global horizontal irradiance, or GHI. That's the total solar power hitting a flat surface, both the clear sky potential and the actual amount considering cloud impact.
Okay.
We also recorded the sun's exact position, its zenith and azimuth angles. That tells us precisely where the sun is in the sky at any given moment, which is critical for panel output.
Right.
Then, of course, the calculated cloud impact on irradiance. And most importantly, the estimated power output for a hypothetical, standardized 100 millidegree solar system in each location.
Why 100 milliW?
Just a standard size to allow for direct comparison between locations. It could be scaled, but using the same baseline makes comparison easy. Analyzing this hourly data let us see those incredibly detailed hour-by-hour patterns, not just, monthly or annual averages.
It's like going from a blurry photograph to high-definition video of solar performance.
That's a great analogy, yeah.
All right, the evidence is collected. Millions of data points. It's time to unpack it. After meticulously collecting all this hourly data, what were the key metrics you extracted? What evidence truly revealed the solar picture for each city?
Okay, so we pulled out the crucial indicators, what you might call the smoking guns of our solar investigation. The big one, the one everyone talks about, is the annual capacity factor.
Right, the famous CF.
Exactly. Think of it like this. If your car's engine could run at full throttle, 247, that's 100% capacity. But in reality, you're not always redlining it, right?
Hopefully not.
Right. So a solar panel's capacity factor tells you, on average, how much power it actually produced over the year, compared to its absolute theoretical maximum, if the sun shone perfectly, 247 at peak intensity.
Okay, that makes sense. What other key clues did you look for in the data?
We also look closely at peak sun hours. This isn't just how long the sun is up. It's the equivalent number of hours per day where the intensity is at its peak, defined as 1,000 watts per square meter. It gives you a better sense of the sun's strength, not just duration.
Got it. Strength, not just length of day.
Exactly. Then there's the variability score. We calculated this using the standard deviation of hourly changes in output. It tells us how spiky or unpredictable the generation is. Is it a smooth, predictable curve day after day? Or is it more like a roller coaster with sudden ups and downs?
Okay, the spikiness factor.
Yeah. And finally, the seasonal ratio. This one's pretty straightforward. We directly compared the average output in the peak summer months to the average output in the lowest winter months. This reveals how drastically generation changes between seasons.
Right, summer versus winter performance. So what does this all mean when you bring it together? This is where your interactive dashboard, your evidence board, really comes into play, I imagine. What was the most striking thing you saw when you first started charting all this data?
Oh, absolutely. What shocked us, really, right off the bat, when we plotted the annual capacity factors by city side by side, it was the sheer gulf.
Yeah.
The massive difference between places like Cairo hitting a really robust 29.5% annual capacity factor.
Very high.
Very good, yeah. Compared to Oslo, which was barely scraping by at 11.2%.
Wow, 11.2% versus 29.5%.
Exactly. That's almost a threefold difference for the exact same hypothetical solar farm technology.
Yeah.
It immediately makes you question that whole solar works everywhere idea, at least from an economic standpoint. The return on investment is just so vastly different.
That is a huge disparity, and I imagine that disparity plays out month by month, too, not just averaged over the year.
Oh, absolutely. When we looked at the monthly generation profiles, charting the output for each city across the year, what truly struck us was seeing Cape Town's output just plummet in its winter months.
Right, the Mediterranean winter rain and clouds.
Exactly. It highlights a massive need for backup power or storage during that time. Compare that to Nairobi, which, despite its 2 rainy seasons, had a surprisingly steady year-round production profile because it's near the equator. You can visually compare these cities side by side on the dashboard charts and immediately see the different planning challenges each one presents. And then there were the daily generation patterns. We looked at typical days, like a day in June for each city. You see the classic dawn-to-dusk power curves.
The bell curve shape.
Yeah, the bell curve. But the scale of those curves, the peak height, varied immensely between the cities.
And these daily patterns, the ups and downs within a day, that's where those solar cliff events come into play, isn't it? How did the data visualize that risk?
That's where the ramp rate distribution analysis came in. Imagine trying to balance a tray full of drinks, like you said before.
Yep.
A gradual tilt is easy to manage.
Right.
But if someone suddenly bumps the table that rapid shift, that's a ramp event in grid terms. A sudden spike, or more worryingly, a sudden drop in power. Our analysis charted the frequency and magnitude of these ramps, how many megawatts per hour the output changed. It showed these rapid changes can be quite common in some areas, particularly those with fast-moving weather systems, like coastal Cape Town. And those are what really make grid operators nervous because they can destabilize the power supply if they're large enough.
Any specific examples that stood out?
I remember tracking one particular CloudFront simulation for Cape Town. It dropped the hypothetical 100 mW systems output by about 80% in under 2 minutes.
Wow, 80% in 2 minutes.
Yeah, it's like watching someone flick a massive light switch off. For grid operators, that's not just a technical challenge, it's a potential emergency. It's a heart-stopping moment.
I can imagine.
We also did a specific cloud impact analysis. This directly connected different simulated cloud conditions, heavy, moderate, light, or clear skies, to the average power output during those conditions. You can clearly see how quickly power drops when even moderate cloud cover rolls in. It's often a much bigger impact than, say, a hot day slightly reducing panel efficiency.
Interesting. So clouds are the real killer.
Clouds are definitely the primary driver of short-term variability, yes.
But perhaps one of the most powerful visual insights from your dashboard, the one that kind of ties it all together seasonally, is that monthly capacity factor heat map. Can you describe that? What does that show us?
Oh, a heat map is a true revelation.
Yeah.
Honestly, it's one of my favorite outputs. Picture a grid, right? You've got the cities listed down one side and the months of the year across the top.
Good.
Each cell in that grid is color-coded based on the calculated capacity factor for that specific city in that specific month. We used a color scale, maybe dark blue for very low CF, going up through greens, yellows to bright red for very high CF.
So you can see the whole year at a glance for all cities.
Instantly. It visually presents how each city performs month by month. Seasonal patterns just leap out at you. You can immediately spot which months are the lean solar months and which are the really bountiful ones for any given location. It's like a comprehensive comparative weather map, specifically for solar performance.
That sounds incredibly useful for planning. So these dashboard visualizations, the metrics, the heat map, they bring us to some truly crucial insights, right? The verdict from our investigation. What are the key takeaways you really want our listener to remember from this deep dive?
Okay, yeah. The big takeaways. First, and we really can't stress this enough, location is everything. That almost 3 times higher capacity factor for Cairo compared to Oslo, 29.5% versus 11.2%. It just clearly demonstrates why saying solar works everywhere is technically true, maybe, but often economically questionable. You simply get so much more energy for your investment in sunnier, clearer locations.
Makes sense. What's number 2?
Second, seasonality varies wildly. Take Cape Town again with that 3.5x summer to winter output ratio. That means you need massive backup power or very significant storage solutions during their winter months.
Huge implications.
Huge. Compare that to Nairobi near the equator, which had a much more manageable 1.2x seasonal ratio.
Yeah.
The need for storage or other complementary power sources like wind or hydro or biomass shifts dramatically based on this seasonal profile.
Okay. Third key insight.
Third, and this was maybe a bit counterintuitive for some, clouds are generally a bigger factor than temperature. London's solar problem isn't really that it's cold, it's that it's persistently cloudy.
Right.
Desert locations like Cairo excel, not primarily because they are hot. In fact, extreme heat slightly reduces panel efficiency, but because they have consistently clear skies. That clear sky advantage far, far outweighs any minor temperature-related efficiency losses. Panels actually perform a bit better when they're cold, but only if they're actually seeing the sun.
That's a really important distinction. Clear skies trump temperature. Okay, and the last key finding.
And finally, this was genuinely surprising to me initially. Variability does not necessarily equal low capacity. Some high-performing cities, annual average-wise, like Cape Town again, can still experience very high daily or even hourly variability due to those dynamic weather patterns, the coastal clouds rolling in and out.
Right.
So even if their overall annual capacity factor looks good, that high variability directly impacts how you need to size your battery storage and manage grid integration. You can't just look at the average. You have to understand the fluctuations.
So what does this kind of granular understanding mean for the bigger picture, for planning renewable energy systems?
It means these deep dive insights are absolutely vital. Anyone planning or investing in renewable energy projects anywhere in the world needs this level of detail. Generic data, those simple averages, they just won't cut it anymore if you want reliable and economically viable systems.
So what's the final verdict from our solar detective right along today? I think you've clearly seen the incredible power of deep diving into specific real-world data, moving far beyond those often quoted generic assumptions. We've tried to show you how it's done, how we approached it, and we want you to know that this dashboard, this data vehicle we built, it's actually a tool you can explore and even customize yourself. Now, hearing me describe this is one thing. Seeing the charts, the heat map, the comparisons, that's really another level. So I've put the entire interactive dashboard, all the charts we talked about, that cool heat map, and even the full Python code notebook we used to generate it all into a blog post.
Yeah.
If you want to see for yourself exactly how Cairo and Oslo stack up visually, or even use the code as a starting point to analyze your own city, Just go to the link in the show notes. You can see everything we talked about today, interact with the charts, and really dig in.
And that's really the core point, isn't it? While solar power is incredibly powerful, it's a crucial part of our energy future.
Absolutely.
Real energy systems demand reliability.
Right.
And that reliability is something that solar, in isolation, cannot always provide, especially given the kind of location-specific variability we've uncovered today. It really highlights the need to consider a broader, more integrated approach to energy generation, which actually brings us logically to our next case.
Yeah, a teaser for next time.
Exactly. In our upcoming deep dive, we'll be tackling something we're calling the biomass paradox. Why we're literally burning money in fields.
Burning money in fields. Intriguing.
Yeah, we'll explore why agricultural waste, things like rice husks, might actually be more valuable as an energy source than the primary crop itself, like the rice.
Wow.
It's a fascinating look at how complementary energy sources, like biomass, can potentially help solve some of these variability challenges we've uncovered with solar today. It's all about finding that truly third-way energy future, which requires looking beyond just a single solution.